This is Mr. Pillar, ECET273, Modern Energy, lecture number 4. We're going to talk about power quality considerations in this lecture. This is focusing on Chapter 3 of the Squarnina DeWitt text and Chapter 6 of the Frodo Patrick text. Power quality issues and harmonics. Those are going to be the two objectives we're going to talk about here. We're going to use some phrases for power quality issues that you're to be using in this course. Things that and typical jargon that is used in normal everyday language to not use because they're not fully definitive of what we're talking about. And we're going to talk a lot about harmonics, the issues that they cause along the line and where they come from. What do we mean when we say power quality? Well, power quality is actually something we take for granted in the United States. We expect every time to turn on the lights will be there, the power will be there, and we complain if power is out for much more than a 10-minute blip. So it's how often do we lose power, the stability of the frequency. We don't think much about that. The frequency in the United States is 60 hertz, and it's fairly solid here. And then there's the presence of harmonics. Harmonics can cause extra loading and overheating of equipment, and we cause harmonics along the line because of devices we plug into the system. So let's begin with the power quality. Show here a voltage line swell. All of a sudden you're running along at a peak of 170 volts, which is our common line current, and we swell up to a peak of 200 volts. Generator comes online, a load gets shed quickly. This happens in industrial park type situations when all of a sudden a bunch of factory machines are shut down. That line swell can cause problems along the line, burn out equipment that's plugged in. So we need to reduce this. Low frequency or high frequency rings along the line. Transients, switching transients. When you turn on a inductive load, there is a voltage kickback. You learned about that in previous courses. This is a power quality issue. Voltage sags. After you suddenly throw a large load on the power grid, we could suddenly have a sag, go from the 170 volt peak as we are promised from the power grid, and then the guy next door puts his big inductive iron on, furnace on, and suddenly there's a drag until it gets to steady state. And the one that we're most used to, the voltage interruption. This could be everything from disconnecting a meter to put a new meter on. I was recently notified by our power company that they were going to come out and install a new meter. They notified us of the power interruption. It was going to happen. Then there's non-notified situations, storms, trees go down, lines fall. These are power interruptions that we need to try to mitigate and reduce. Terms to be avoided. Blackouts and brownouts. Generally speaking, blackouts are termed power outages. Power outage is the proper term. A brownout would be the voltage sag. Everybody turns on their air conditioners all at noon, and suddenly the voltage drops out a bit. We don't want to use this term. Dirty or clean power or dirty or clean ground, not a useful term. Not accurate if everything is wired appropriately. Ground is ground. So there is not a clean ground specifically in a system. You should have only one ground. Power surge. That's non-descriptive of an issue. You have a voltage spike perhaps, but what is a power surge? A dedicated ground. Again, another problem. Not accurate in the system. A spike, voltage spike. Again, we would call that a transient. So that's with power quality. And associated with power quality more specifically is the level of harmonics on the system. Harmonics reside not only on the voltage but on the current. Ideally, we'd have single frequency sinusoids. Straight off the generator, it's a natural straight off system. We have a clean sinusoid. But with the electronic world that we have today, we are switching power supplies, diodes, rectifying AC to DC, DC to AC systems. We end up creating noise on our line inadvertently to produce those waveforms, and you have multiple frequencies that divide up our actual fundamental signal that we're looking for. Harmonics are the signals that present the whole frequency as an integral multiple of the fundamental frequency. So basically, with the dark bold line here, that's what we refer to as our fundamental. That's our intended signal we're looking for. But if this is not a pure whole sine wave, it is built up of first, second, third, fourth, fifth, go all the way up order harmonics. Actually, we're going to come to find out that it's mostly the odds, not the evens. But each of those is a multiple of the frequency of the fundamental. And we're talking Fourier series here. Okay, so here's an example of a square wave in the Fourier series for a square wave. The equation will always end up with odd numbers, so 1 over 3, 1 over 5, 1 over 7, 1 over 9. You've done this before, so I'm not going to go deep into it. This is a previous course, or a parallel course, but this is what we're talking about. So how are we going to identify the size of the harmonic content in a waveform? Well, that is the total harmonic distortion, the THD. There's two ways of defining this. Generally speaking, the US uses one way, the rest of the world uses the other, and it's the difference between the two is the defining ratio. The THDF, the total harmonic of the fundamental, would be the sum of the harmonics divided by the fundamental itself times 100%. So it gives a percentage of harmonics versus the fundamental. The RMS would be the total harmonic distortion of everything of the RMS value of the waveform. Fundamental included in there. For our purposes, we're going to use the THDF. Well, how do you find the VRMS? Well, the VRMS is equal to the square root of the fundamental squared plus the third squared plus the fifth squared plus the seventh squared plus the ninth squared plus all the RMSs that we have available. The THDF would drop off the fundamental RMS, and you take all the odds and you do the square root of that, the summation of the square root of all those odds, and divide it by the RMS of the fundamental. The THDR would do the same thing, but rather than dividing by the RMS of the fundamental, you divide by the total RMS. Now here's our gotcha. Who cares about the harmonics? Well, each harmonic has a sequence. It has a positive, a negative, and a zero sequence. The positive sequence cancels each other out because they're all out of phase. The negative sequence cancels each other out because they're all 120 degrees out of phase. But a zero sequence becomes additive. And here's the problem. The triplet harmonics are zero sequence, and so they're additive. So harmonics that are divisible by 3 become additive and sum up. The currents would sum up on the neutral in a Y system. And that's where we run into an issue. We could actually get to a position where we have a highly harmonic load, and our neutral current ends up being greater than the individual phase magnitude currents. And so we need to mitigate that issue or properly size neutrals or increase size of transformers because of the presence of these harmonics that may be presented as loads in our system. So summary, we have power quality, we have words that we use in everyday language, and then words that we need to use in this course and other engineering purposes. We now know harmonics are caused by nonlinear loads. We're going to get into what nonlinear loads mean, but they are caused by nonlinear loads, basically the transformation of AC to DC. A harmonic is a component of the fundamental. THD is a way of telling the percentage of harmonics available there. Harmonic sequences, when we have a zero sequence harmonic, which would be the multiples of 3 harmonics, we call triplets. They're additive, and they increase the current that we see on the system outside of what would be determined by strictly the load.